then we can start to calculate the delta G. Okay, so you know the G is written in this way, right? Then the delta G will equals to your summation mu I dni. Okay, so this means the change of your reactant or product in moles, right? And we know dni can be written as d epsilon vi. That's your delta G. Okay. Therefore, you can define a quantity delta G d epsilon I is going to be equals to summation mu I times vi. Okay. So what does this mean? This means how the delta G is going to change when your reaction proceeds, because the bottom one represents how complete the reaction is, right? So this means how your delta G is going to evolve when the reaction is proceeding. And then this term is going to relate it to your chemical potential of each individual components times their stoichiometry coefficient. And if you sum them all up, that's the whole thing for your system. Okay? And again, these terms can either be positive, 0, or negative, right? When it becomes 0, that means the reaction is actually complete, right? It reached the equilibrium state. Then you're going to have delta G over delta epsilon equals to 0 at equilibrium. Okay? If it's negative, that means the reaction will continue move to the product side. And if it's positive, that means the reaction is going to move to the reactant side. Okay? Okay, so far we use this mu I concept for a long time already, right? And you should be very familiar with that for any given system, because it's ideal gas, non-ideal gas, ideal solution, or non-ideal solution, you can always express the chemical potential of one specific component equals to mu I naught plus RT natural log AI. Okay, so this is always true no matter what condition you have. Okay, just for different conditions, the expression of AI will be different. Okay. So previously we say, okay, the G is equals to summation Vi mu I. Okay, so if you put these things into this equation, what you're going to get is actually the system G is going to equals to summation Vi mu I naught plus RT summation Vi natural log AI. Okay, so this is the Gibbs free energy of the whole system. Okay. So you should see this, the first term, okay, is summation Vi times Vi naught, okay, and this is actually your delta G naught, right? Because it's all under standard states, and you're taking into account all the species and their stoichiometry coefficients. Therefore, this term is going to equal to your delta G naught. Okay? For the second term, you can put the Vi into a natural log, so it will equal to RT summation natural log AI to the Vi's power. Okay? Sorry. Okay. So this term you can rewrite as RT natural log Q. Okay. And you can have a general expression that if you want to describe a Gibbs free energy of a system, okay, regardless of what kind of system you have, the G is going to equal delta G naught plus RT natural log Q. Okay, the Q is called the activity quotient. Okay, it's called the activity quotient. Okay, what it means, if you put in all the activities inside at any given state, you can calculate a number of Q. Okay? Only when your systems reach equilibrium, the Q is going to equals to your equilibrium constant. Okay? So also you will know, once you reach equilibrium, then you know your delta G is going to equals to 0, right? So this will be delta G. Okay. So this is 0, right? Then you go back to delta G naught equals to negative RT natural log K. Okay, so once equilibrium Q equals to K, then this equation will become best. To rearrange that, you go back to this equation again. Okay? So apparently you need to know how to write the activity correctly for different systems. Okay? So what is the A for different conditions? We actually mentioned this one 2 days ago, right? So for the gas systems, if you have ideal gas, your A is going to equals to P over P naught. For non-ideal gas, your A is going to equals to your gas D over P naught. For the pure liquid, pure solid, the A is just equals to 1. Okay? And for your solution, okay, this is the part you need to be a little bit more careful because the conventions is somewhat misleading. Okay? When we talk about a solution, when you deal with the solute and solvent, they actually looks like differently. Okay? For your solute, the A is defined as N over N naught. Okay, so you will see in all the questions you encounter in your homework and your final, okay, it will always tell you the concentration of your solute is how many N. Okay, so that means you can calculate your activity using this equation. Okay, so this is very important equation for all of you. Okay, and all the solution you're going to encounter this semester, it will be all dilute solution. What it means is inside your system, inside your solution, majority of them is actually your solvent, not the solute. Okay? So if you use molality to express the activity of your solvent, then you get a huge number. Okay? But you will never see that, okay, in real life. The reason for that is because when people define this is the solvent, not solute. When people define the activity of your solvent, they actually use the mole fraction rather than the molality. So this is the conventions, okay, people always use. Okay? So for your solvent, the A need to use more fractions rather than molality. Okay, this is very important. Okay, and because it is a dilute solution, then you can imagine your mole fraction for your solvent will be 0.9999 something. Okay, so this will be typically just equals to 1 for your solvent. Okay. Give you one example. Okay, if you have 1 kilogram of water, okay, that's going to equals to 55.6 N. Okay, so it's actually, if you express the concentration of water in molality, that's the number you're going to get. Okay, but if you look at your questions inside your homework, okay, the concentration of solute is like what? 0.01, 0.005, right? So if you compare these two quantities for your solute, in your question, typically you have 0.1, that's pretty high already, okay? If you compare these two, you can see the mole fraction of this one will be really, really high and very, very close to 1, okay? Therefore, people just say, okay, for dilute solution, the activity of your solvent is just use 1. Okay? So this is important when you solve the questions. Okay, so